I think recording is started. So let's start then today's class. So let me first briefly recall whatever we learned in the previous class. So in the previous class we learn a paradigmatic game whose name is prisoner dilemma, and we have seen what dilemma is there, why rational individuals who wants to maximize their payoff will always fall for the minimum amount of payoff, suboptimal payoff. And we are trying to find out whether or not to get out from that such dilemma, and how one of the way out to such dilemma we thought in the previous class, or we learned in the previous class. One of the way might be repeated interactions. Because of repeated interaction, maybe uh, we could avoid such dilemma. So that is the first thing. Then we came up with one example of repeated one example of strategy which one can play in repeated prisoner dilemma, and sometimes this strategy can win. However, this is called the Grimm strategy. The Grimm strategy means the cooperate in the first round and uh, and remain cooperating, means and cooperate means do not defect until you see your opponent defect. So that is the Grimm strategy. And there is another strategy which is Aldi strategy. That means no matter what your opponent do, you should do defection. So we have to see whether or not this Grimm strategy this Grimm strategy can invade or these Grimm strategy is yes or not. That if there in the population all the individuals are playing using Grimm strategy, any small amount of mutant of Aldi can invade the population of Grimm or not. So that is our goal. Now we have seen that if they play m times the game, then if m is larger enough, then and there will be a case where the Grimm could be a evolutionary stable strategy. Now we find that Grimm has several problems, and one of the problems we have we came across, that the problem is that if that suddenly one some other strategy comes which is almost likely Grimm, but since at the last step, since there is no more further interaction, they will not meet again. That's why they will try to defect, and this is called Grimm star strategy. Now we see that Grimm star strategy uh, will invade a population of Grimm, and if we follow the same thing through and make another strategy which is called Grimm double star, that means instead of why stopping at defection at the last step, why not defection at the last two steps. And if I follow this reasoning, we will all trap in the again all this strategy, which means no matter what my opponent does, I will do defection. Now again again we have talked about that people um, uh, people by doing experiment with these kinds of game and with humans, people well documented these results. So one of the result is that individual may tempted to defect at the last round. That means Green Star is alright, but they do not follow the reasoning altogether up to the Aldi. That means people may be tempted because it is their last interaction. Maybe they could think like that, why not? Since we are meeting at last, so against a Green player, why not in the last round take a chance by defecting? Maybe I will get more payoff than whatever I was getting in the previous round. So Grim Star is alright, but after the Grim Star, they will not logically follow the step that after Grim Star I could do one thing also. Why Grim Star? We should we should defect at the last two round also. This kind of logical consequence people don't find, that experimentalists found in their control lab system. Now this is the things. Now why, if we ask the question, why human beings not uh, not do these kinds of um, reasoning to came back to the oldie. Now one of the reason may be, there will be many more reasons, but one of the reason may be humans decision making faculties does not evolve in interaction which is is a finite number of interactions. So what does I mean? So what do I mean? That means that human, the number of interaction, when the interaction will end, maybe we evolve in such a situation we don't know that this interaction will end after finite number of steps or finite number of interaction. It may be happen, so there may be a next interaction at tomorrow, I don't know. So this might be the case. That's why human don't want to defect, don't want to defect at the last round, because the humans don't know actually what will be the last round. That's how we evolve in the nature. So if we consider, if we consider that factor also, that means that tomorrow never dies, that we don't know up to which, means we don't know exact number when our, what is our last meeting, or what will be our last encounter, or what will be our last interactions. So since we don't know, so that means we cannot cheat at the last step because we don't know the last step. uh, this is the thing. So let us consider this thing in our formalism.
So I have a
Hmm.
query here
Hmm.
that in the green star,
Hmm.
so from the evolution viewpoint,
Hmm.
is this similar to the situation that a sudden mutation
Hmm.
occurs in the
Hmm.
species, and quite possible that that may result into a specific kind of the species? Like say in the green star.
Hmm.
So I mean, even before the opponent
Hmm.
makes a defect,
Hmm.
I make a defect first.
Hmm.
This is the case. And in the green star,
Hmm.
I make the defects in the previous two
Hmm.
positions. So is this defect, all of a sudden defect is similar to the mutation in the among the species?
Yeah, you are right. Means you could think like that. Evolution is not only on the species level. You can think also in the level of cultural level. So in the cultural evolution, you may find in some society they are try to more following the cooperative things, that cooperation, and in some society the societal norm is like that they wants to defect much more. So yes, it could happen, so that you may find due to the cultural evolution. And I want to add one thing, that you are asking, you are asking the previous class what kind of, in the what kind of scenarios we can use these tools. So one of the thing is where you can use the tools is cultural evolution. So how our culture evolved, and the culture means culture means, you know, that what kind of behavior I will show when I will meet with another person. So these can be also thing like a evolution, which is called the cultural evolution. In the context of cultural evolution, you can see this type of strategy is automatically evolving in the in certain culture. So species, I don't know, because for the species, is, for the species I don't know actually, that this kind of thing will evolve in the long run. But we never seen the, I mean, this is purely theoretical stuff. So for the moment I cannot give you an example where these can you means these things can happening in nature and species.
Okay, okay. Thanks.
So let me, since, and the thing, another thing is what I was discussing, that one of the main reason maybe why you cannot see those kind of thing because here in the theoretical purpose you are saying that there is a serpent, but in the physical world no one knows that when will be our last meeting, when will be our last interaction. So basically we could not, we means there is no capability, no when, what is our last meeting. So maybe that is also a possible reason why we will not adopt. If we may think like that, that in the last round the defection may be a good strategy, but we don't know what is the last strategy, last round of play. So is it clear?
Yes, yes, it is clear.
Okay. So now that means uh, after playing a one round, so
So I have a query here.
okay.
So does this mean that we need not to wait till the end, and any strategy wherein we wait till the end won't be appropriate. So rather we should keep on doing something ongoing. Like the yesterday you mentioned tit for tat kind of a
Huh.
strategy.
Hmm.
So I mean that is more appropriate because I need not to wait till the end.
Yes.
Whatever my opponent is doing, and
Huh.
I will give a befit reply to my opponent. Is
Exactly,
this
exactly. We will find
okay?
that you are right, that in this thing that we will see that the tit for tat is a good strategy for playing this kind of defeated game. So, and one thing I want to say that your voice is too feeble, means I cannot.
Okay, so I will change my device
Okay,
immediately.
okay,
No issues. You please continue. I will change my device
okay.
immediately.
Then the thing is that tomorrow is never dies. That tomorrow never. So this is the, now instead of thinking that we will have particularly m number of interaction, let us think that every that uh, that study rather than a fixed number of rounds, suppose that after each round, after each round, suppose w is the probability of happening of next round. So if we play this round, then only we know the probability that with some probability there may be some other interaction between us may occur. So we know only the probability, not the number of rounds we are going to play. We only know the probability. With that probability, the next round may occur, or and with 1 minus w probability that next round may not occur. Now let us calculate on average, if this is the case, then on average how much payoff or we will get if we interact with each other. Now to know that on average interaction, so let us calculate how on average how many round is possible if w is the probability of playing next round. So then after playing first round, the what is the probability of playing first round? That will be 1. What will be the playing second round? That will be w. What will be playing the third round? That will be w square. Then what will be playing n round? That will be n minus 1. Now if I say that after nth round I will not, after nth round the game will stop. What is the probability of that? If what is the probability that after nth round game will stop, game will stop. So for this I have to play successfully nth up to nth round. That means this should be the probability that game will go to up to nth round, and then after nth round what is the probability that game will not proceed further, means there will be no next round. So that is the probability that our game will stop at nth round. So then what is the average number of step or average number of round we are playing with each other, that will be, so this is the probability of happening nth round of interaction. So I have to sum over n equal to 0 to infinity, then I will get the average number of interaction. So suppose that average number of interaction is n bar, and then let us see what it is. N if I equal to 0 to infinity n wn. Now the summation of this series is this n equal to 0 to infinity n wn. The summation of this series is 1 by, this series is not, this series is w by 1 minus w to the power square. So then it's come out 1 minus w into w by w square. So that means average number of round that the game will be continued, that is 1 minus w bar. So the how much on average I will get the payoff. So let us calculate for the green. Already now this will be simply in place of whatever last calculate in place of m, since now I want to calculate on average how much I will get, then I have to replace this m by average m, and or maybe in place of n write it m, then it will be fine. M, this will be m, this will be m, and this is m bar. So m bar into r, and in case of already this will be s. At the first round green will get s because the already defected, so that's why, and on other round the green will get t, and here in the first round it will get t, and in the other round it will get p, and here it always get p. So this is up to now, is it clear?
Yes, it is clear to me,
Okay.
and I hope that my voice is okay.
Yeah, now it is clear. Now that means again the from here we can calculate the what will be the probability, that means m bar has to be greater than t minus p by r minus p. Then we can see that green is an evolutionary stable strategy, or maybe means this condition is comes from the ordinary relationship between these two pair. So m bar r, so m bar r has to greater than t plus, this would be m minus 1, this would be m minus 1 p. So this relation will come from here, we will get m bar has to greater than t minus p by p. So from here you will get 1 minus 1 by w greater than t minus p by r minus p. If I know there is a enough probability of meeting again in the next round, I have to play the green. But the green is, then we solve the problem that there will be no tendency to defect at the last round, because we don't know what is the last round. Now another problem with green is that green is alright, but green is a little bit strict. Why? Because if my opponent for only once play defect to see where how much payoff he will get, and after next round he start to cooperate again. But the green is so strict because he because the green sees that her opponent defect only once, he will not forgive our opponent, and he will continue to defect forever. So that is not a good strategy to play against our opponent. So that is another problem with green. Now this is only one example we are seeing here. Now what are the other strategy that could be possible in this repeated prisoner dilemma? Let us see that. So what do I mean by the strategy? Let me define what is mean by the strategy. There are two, there can be two type of strategy. One is deterministic and other is stochastic. So let me first see what is the deterministic strategy. Now you see, this is our prisoner dilemma game, or is TP, here C, here D, C, D. So after every round of play, I will see this kind of outcome, CC or CD or DC or DD. So maybe I play cooperation, you play also cooperation here. Here I play cooperation, you play defection. I play defection, you play cooperation. I play defection, you also play defection. So these four thing can be possible in one round's outcome. Now here strategy means, a deterministic strategy means I will decide that I may decide that, so if CC comes, I will cooperate. This is the deterministic strategy. So CC come, I can choose, I will choose cooperation. If CD comes, I will choose defection. I DC comes, I will choose again cooperation. I DD comes again defection. So this is one of the strategy, deterministic strategy. So I
Yeah, I have a query that what's the meaning of that CD comes?
okay. So if two player is actually playing the game, so after one round, what kind of outcomes is possible? One outcome is I play C, you play C, and we will get something. So after one round, the outcome will be C and C, the cooperation. These are the actions of player 1 and player 2.
Oh, I see. So so does this mean that this string CC, CD, and DC and DD? So these are the strategies played in the previous round, and based on the
Yeah.
outcome of the previous round, and now I'm deciding that in the previous round, if you cooperated and I also cooperated, then I will continue the cooperation.
Hmm. Hmm.
And okay, so now I understood. Yeah,
Okay.
fine.
So this is one of the strategy, one of my strategy. Now it could be anything else also. Maybe here D, here C, here D, here D. Maybe also this all D, everywhere all D also comes here. Now guess how much how much deterministic strategy is possible here? Exactly, total 16 possibility. Here total 16 possibility, 16 possibilities. That means 2 to the power 4 possible deterministic strategy only. Now if I only see the outcomes of the previous round, now if I say I want to determine my deterministic strategy based on previous two rounds outcome, then what it will be? It will be 2 to the power 4 to the power 4 square, 2 to the power 16, because in the previous round 16 outcome possible, and since 16 outcome possible, my strategy now, my number of deterministic strategy will be 2 to the power 16. So if I now decide I want to see mth round of interaction, then mth round of mth round of interactions outcomes, after that I will decide my strategy, that will be 2 to the power 4 to the power n. So it means that it is it is very large. If I see only 2 round, it is 2 to the power 16. So then the state space of the deterministic strategy is very large. Now let's see about the stochastic strategy. Now stochastic strategy means that if I see cooperation, I will cooperate with probability q, c, and I will I will decide cooperation with qc probability and defect with qd probability, or maybe 1 minus qc is same. So qc probability. Now if I see cd, I will maybe cc, I will cooperate with cd probability. Or if I see dc, I will cooperate with probability q dc maybe. And if I see, let me write it in terms of p, then because of later on you may be confused with the symbols. If I see the outcome cc, I will cooperate with probability pcc. And if I see cd outcomes, then I will cooperate with pcd in the and if I see a DC, I will cooperate with PDC and DD with probability PDD. So these are my now strategy: probability PCC, the probability PCD, probability DC, and probability DD. And this probability can be, these probabilities can be a number between 0 to 1.
I have a query here that if the probability of operation is PC, then what is the other strategy? Like say I would be cooperating with the probability of say X. Then with the probability of 1 minus X, what else my action be?
Defection.
I see. I see. Yeah, right.
So, but here the strategy means whole set of these four numbers. The four number is one strategy. Here not only one number is strategy, mine strategy. Since the four outcome is possible, so these four numbers are my strategy now. Now you see, if I see only one, I will that four dimensional space, where this four dimensional space means x, y, z, and maybe w. So there are four dimensional spaces there where my strategy remains. Now if I increase, if I see only last step, means if I see only the one outcomes, now if I want to see the last two outcomes, then my strategy pace will become 16. And if I want to see the m last outcomes, depending on that I will select my strategy, then the strategy space will become q to the power m. So you see there will be lot of humongous strategy are there, infinite number of strategies is there. So there is, means it is very hard to put these things in a computer and let's computer to calculate what will be the optimal strategy to play repeated prisoner dilemma. Because you see, in case of deterministic strategy also and in case of stochastic strategy also, the number of strategies is very high. So you maybe miss some strategy if you want to use some computationally, you have to put some bound. So maybe that is the reason that it is very hard to get with some strategy which is optimal. Now to deal with this problem, there is famous uh, political scientist at University of Michigan at Ann Arbor, uh, has a brilliant idea whose name is that Robert Axelrod. Robert Axelrod came with a brilliant idea, brilliant and simple idea, that he invited people from around the world and he means make a prisoner dilemma championship, where that he invited scientists and all game theorists and all scientists from all over the world to submit their strategy to win the prisoner dilemma game. So this is his strategy. Now instead of doing by himself, he just build a competition. Now interestingly, people in the first tournament of the prisoner dilemma game from the all over the world, there are 14 contestants were there, and Accelerate says that your or means the condition was that the contestant strategy should be in such a way that it could be written in computer, so that in computer maybe this kind of game they could play this kind of game, and after some round means they can sum up the all payoff or the strategy gets, and after some rounds they may say that who is the actual winner of the game. Now here out of all these games, who is the winner? The winner is tit for tat. The tit for tat strategy was submitted by a known theorist is Anatole Rappaport, who first submitted this tit for tat strategy. And what does this tit for tat strategy? Tit for tat strategy is very simple strategy, and tit for tat is that I will start with cooperation, but in the next round I will do whatever my opponent did in the last round. So simply I will start with cooperation, but after that I will do whatever my opponent does. If my opponent did cooperation, I will also cooperate. If my opponent did cooperation in the last round, I will observe that I will cooperate in the next round. If my opponent did defection in the last round, I will do defection in the next round. This is the simple strategy, but I will always start from cooperation. Now Axelrod published his result together with a comprehensive analysis and shows that TFT is the champion of this of the previous tournament. Now he again announced another game, another tournament. Then 63 strategy came from all over the world, and out of the 63 strategies there was okay.
I have a question here.
Hmm.
That what was in that competition?
Hmm.
So, what was the purpose, and what the people were trying to maximize or minimize?
Okay.
What was their goal?
Uh, their goal is simple, to get the maximum payoff. So RSTP, they are their strategy will play this game repeatedly. Suppose this is the my criteria that after each round the probability of playing the next round is W. The next round is W. This is the thing. I will say these things in computer, and they submit a strategy, and this strategy will play this game against another strategy. Another strategy submitted by another individual, and every strategy will play against every strategy. And how much uh, payoff, or how much payoff they accumulated at the last, that means this is calculated how much payoff he get. So if the games continue to mth round, then this type of payoff I am computing, and I want to maximize it in such a way that my payoff will in the long run will be evolutionary stable, or the maximum payoff.
So only the payoff or the sum of the payoffs. Like say, if I am the player towards the row side,
Hmm.
then I would like to maximize the sum of the
Sum of the
payoffs
payoff.
I received in the first row. I mean, my strategy. I mean, I should get the maximum payoff.
Hmm.
The other player may use different
Hmm.
strategies, but then. So my question is that can you please go to that
Hmm.
payoff matrix?
Exactly.
Uh, yeah, this one.
Hmm.
So here, what is my goal? Say if I am the player G,
Hmm.
then in that competition was the goal to get the maximum value of MR plus M minus 1 R plus
T.
S, or merely MR.
Oh, okay. Acha. No, my goal will be that I will choose such strategy that in the game theoretic sense, it is a Nash equilibrium, or maybe it is evolutionary stable strategy. So here I want to make such a strategy that will in long run will sustain. That means these things should follow, that if I compare against my strategy, no other strategy will get maximum payoff. Maybe with my strategy, if I play with my strategy, I will get the maximum amount of payoff. Hmm.
I see. So the value of MR should be the maximum one and not the sum of the first row, is it?
Yeah, not the sum of the first row.
Okay, 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 fine.
So means whatever I am saying in this context, it is the evolutionary context. So my strategy will be optimum, means my strategy will be ESS, or evolutionary stable strategy, in a sense that if I play against means my strategy play against my strategy, it will get MR. But if any other strategy play against my strategy, it will get less than that my strategy. Then there will be no incentives to deviate from the my strategy. So then this my strategy is be ESS kind of thing. So different from all D. All D will be always ESS, but different from all D, what could we do best?
Actually, the confusion arises here because now instead of the players,
Hmm.
actual players,
Hmm.
instead of the two-player game,
Hmm.
here the game is being played in between two strategies.
Yes.
So now, since there are two strategies, then who is the opponent?
Okay. The
So,
okay. Opponent maybe you can think like that. Opponent is playing that strategy.
oh,
Opponent.
I see. But then whenever we say that Aldi or any other strategy,
Hmm.
the opponent is using something, and opponent is not bound to follow anything. Opponent
Exactly.
is making the natural choice, and only I am the one
Hmm.
who is responding based on the behavior of my opponent. If opponent also started playing some strategy, so then it would be a bounded situation kind of the thing wherein I am following X1 strategy, the other is following the X2 strategy. The more realistic thing would be
Hmm.
that the other party is free from following any strategy, and I am the only one who respond based on the I mean the the action taken by my opponent.
No, you see, you are right, but it is actually capture. No, here at first I am analyzing the situation from my point of view, but my opponent also see from his point of views. But the since the game matrix is symmetric itself, then he also finds the similar conclusion that I actually find. So if I find to play Grim is best against Grim, he also find the play Grim against Grim is best. So he will not find any motivation to deviate from the Grim.
Oh, I see.
So
Yes, now
means
I understood. This
in,
makes sense
hmm,
here.
instead of writing this, if I write two pair of matrix, means since I have introduced the concept of these things, so that's why I just skipping those part. But you are right; these two player actually deciding what is going to happen, or this is from the classical point of view, and evolutionary game theory point of view. There is a population whose in the population you may find that X fraction of Grim is present, and rest of the individual may be Grim star. Now you see if the the system evolve at the long run, what you will see.
Yes, yes.
So now what was I that they again in the first championship, the TFT was the champion, and uh, then again the second round of the championship was announced by the Axelrod, and that time the 63 contestant give their strategy, and there was one strategy that was called tit for tat that was submitted by the John Maynard Smith, who is the founder of this evolutionary game theory. However, in this round also, the tit for tat was the only champion, and the tit for tat was filled by the rapport, Rappaport, who was first submitted the TFT. Now here also the TFT won, and Axelrod published a book which is called the Evolution of Cooperation, which was a bestseller at that time, and the TFT was the unquestionable champion in the repeated prisoner dilemma that was played at that tournament. Now Axelrod praises TFT because of two reasons. One is that TFT is nice in a sense. TFT is nice because TFT never never defect fast. TFT always cooperate fast. So TFT in the first round they will always cooperate fast, and that is one the nice property. So they will never do defection at first. And the second property that TFT does not want to uh, maximize his payoff in the pairwise comparison. Means I am saying that TFT just want to play to want to get the payoff his opponent actually getting. So if his opponent is playing D, he'll also play D. That means he wants to remain in the regime where the both will get the same kind of payoff, mostly same kind of payoff, but the winning of the TFT remain in the thing of that the when we summing up and we average all the round, then the TFT will win. So let me give you the mathematical concrete exam. You will see that why TFT is winning against almighty Aldi. Let's see the TFT and TFT Aldi. Now TFT and Aldi's payoff matrix will be similar to the Grimm and Aldi. Let me show you why. So here the TFT will be cooperate fast, but Aldi will first in the first round he will defect, but as soon as the TFT sees that Aldi defects this defection, he will start to defection, and since Aldi never do cooperation, that means this defection will continue. So that means when a TFT play against Aldi, he will get, if suppose that on average mth on average ember round they play the game. Why this on average? Because we are want to see that there will be no last round. Only we know that after each round W is the probability of the next round, and if it is the case, then there will be on average ember round, a game, a repeated game could be going on. So ember will be that. So when a TFT play against Aldi, it will get in the first round he will get S, and the rest of the round will get P. So that means here S plus ember minus 1 into P. Here Aldi will get T plus ember minus 1 into P, and Aldi will always defect, this will get D, and TFT always get ember into R. Now you see that the game matrix is similar to the Grimm, and here also with ember you will find that ember R, when ember R will be greater than T plus ember minus 1 into P.
Probably I missed this thing. What this M complement used to be? What this M complement is?
Oh, is the average number of round. So if W is the probability of happening next round, so and 1 minus probability of being stopped at the next round, then what will be the average number of step we will play. So I have here the what is the probability of playing first round, that is 1. What will be then probability of playing second round, that is W, and third round W square. So what will be the probability of playing nth round, that will be W to the power n minus 1. Now what is the probability after nth round the game will stop, that will be that I have to play nth round, then I have to stop. So what is the probability, that will be probability W to the power m minus 1 and m minus 1 and 1 minus W, this will be m. So 1 minus W, and I played mth round. So what will be the average? So m into the probability, that will be average. Is it clear?
So
Hmm.
till here the thing is clear that w raised to the power m minus 1,
Hmm.
1 minus w,
Hmm.
and this is the probability of playing
Huh.
the mth round.
Huh.
So then why are we multiplying this thing with the value m?
So how do we calculate the average? So
Oh, I see. Expected value kind
huh,
of the thing.
average expected. What will be
Okay.
the expected number of these? This is m, and if you do, you will get simply a series, and the series comes out this, and the result will be 1 by 1 minus w.
Yeah.
So
So what? Okay. So 0 to infinite
hmm,
kind.
hmm.
Okay. 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 Yes. Yes. Right.
then then I am saying that since there is no tomorrows, the game is playing only probabilistically, not there is a serpent, then on average what will be the expected number of round I will play? That will be m bar. So
Yes.
then how much payoff if I play on expected m bar round, then on expected how much payoff I will get? That is here I have written this is. So then when the TFT will win when m bar r is greater than t plus m bar p. So this means if m bar r minus p will greater than t minus p, and you see if m bar is greater than t minus p by r minus p. So if they repeatedly play, and maybe the probability 1 minus 1 by w is t minus p by r minus p. So if there is enough probability to play the game again, then we may find that the TFT will win. So that is the case. Now that's how TFT actually win the battle against the Aldi. Now here the problem that was faced by the Grimm is not present. That in TFT case, uh, it could forgive one defection of the opponent. How? If some it start with cooperation, in after some point of time, maybe her opponent thinks that I just want to see what defection will give me, and after that he find that it is very bad to defect, and he start to cooperate. So initially this TFT since in the last round sees a defection, it will defect, but in the next round, from the next round, it will start to cooperate again. So that means TFT can forgive only one mistakes of the our opponent, but in the Grim don't have that forgiveness, and that's why TFT is better than Grim. So up to this much, if it clear, then we can go further.
Yes. Yes.
Okay. So now the question is the TFT don't has any problem? Is TFT is problem free strategy? No, the problem is TFTs has several problems. Now let us talk about the TFT's problem. TFT's problems. So what kind of problems TFT is here? So where what does Axelrod does in his did in his experiment through a computer, that is in the digital world, which is completely error free. Now in the real world that is not the case. By playing means when I just if my study is TFT, I could mistakenly in place of C sometimes very with some probability, I could play mistakenly for C. In place of C I could play D. And in other words, if I misjudge my opponent's move in the previous round, and I could wrongly play something. So TFT with some error, let us see what will happen if TFT with small error, very small error. So TFT means two TFT player is playing against each other. TFT. So at the first round they will play C, and since he will see C, she will play C. At some time maybe some error happens, and some error happens since it C in the previous round it's C. Now it will D C, because in the previous round it is C. Now here it will play D, and again D C, and here C D D C. So this type of sequence will goes. Now after again one mistakes that could lead to all defection. So here suppose after here maybe this is maybe defection, then means mistakenly the second player did a mistake, d star in place of c he plays d star, then you see that d persists and d persists until another mistakes happens. Now in this case you find with small error TFT, you will find this kind of chunk. So C in this chunk it will get a pay of R, and chunk in this chunk it will get a pay of S plus T by 2, because in some round he will defect and it will get T, and some round it cooperate it will get S, and in other round it will get P.
So in this case, are both the players playing TFT?
Yeah, both the player is playing TFT.
Oh, I see. I see.
Now, in place of getting R, in 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 presence of mistake, they will get this much pay of R plus S plus T plus P by 4. So, as if they are in place of mistake, as if they are playing randomly with probability half by tossing a coin with probability half and choosing, if the head comes he choose cooperation, if tails comes he choose defect with probability half, and it does not depend on the what opponent did in the previous round. It almost it almost gives the same payoff as a random strategy with half probability cooperation and half probability defection will give. So this is the problem, because this is actually less than the R. Why it is less than? Let's see. This is less than R because you see R plus S plus T plus P is less than 4R, and S plus T plus P less than 3R. Since P is always less than R, then means we can write it S plus T less than 2R. Is it the case? Yes, for the prisoner dilemma, S by 2 by T has to be less than R. So that means in this case, what 2 DFT is playing, they are getting less amount of payoff in presence of tiny bit of error, and in the error free regime the TFT will get the P of R. Now this is the problem, that the TFT cannot cannot erase if some error comes in their playing strategy. So this is the one problem with the TFT. Is it fine?
Yes.
Okay. So this is the problem. Now this is the one problem. Now we deal with this problem little later. Now first let me introduce. Okay, why it is not working? So up to now whatever we talk, that is, let me my, so up to now whatever we talk is called the reactive strategy. Why it is reactive? Because I give a reaction to my opponent's previous move. So whatever my opponent did, I will reciprocate that. The TFT is the best reciprocal strategy that anyone could play. Why my eraser is not working? Okay, let me again open it, then maybe it will work. Let excuse me for a moment because my pen tab is not working.
No issues.
Okay, now it's working. Yeah, now whatever we did is called the reciprocal strategy, because I am reciprocating my opponent, means, and the TFT is the maximum reciprocal strategy one could achieve, because I am doing whatever my opponent did in the previous round. So this is called the reciprocal strategies. Now I will let us talk about that reactive strategies. Whatever we did, it is called the reciprocal strategies. Now let us talk about reactive strategies. Then I will talk about that is there any strategy which actually can be such a way which win against TFT and all D, and which also can forgive some error if her opponent does while playing against it. Now the reactive strategy. Reactive strategies. Now, since we have already in the previous case we done with some calculation with some deterministic strategies, and we did actually for deterministic strategy like TFT and Green and ALD. Now let us introduce an reactive strategy which is a stochastic strategy. So, if we want to write a stochastic strategy after observing what was the previous round outcome, it will be it will the calculation will be little bit difficult. Now let us first use one strategy not which only observe my opponent's move, not my previous move. So that means if in the previous round outcome of CC, I only suppose this is I and this is you maybe. So I will observe in the next round, this is previous round. In the next round I will observe only your move, that is C, and if I see in the previous round you cooperated, I will cooperate with probability suppose P. I will probability P, I will cooperate if you cooperated in the previous round, and with probability Q I will cooperate if you defect in the previous round. This is called the reactive strategy. I am reacting to your strategy stochastically. So is the strategy clear?
So in the strategy, what this P is that if the other party cooperate, then
with probability P I will cooperate.
Okay.
And if the other party defect, with probability Q I will cooperate. If other probability
reverse. So I'm taking reverse of the and not tit for tat. Why so?
No, tit for tat is deterministic strategy. Now let's talk about the some stochastic strategies.
Okay, fine.
Now with this notation you actually could find our previous known strategies. So now our strategy become P and Q. So if my opponent cooperate, that will be my strategy. Now if my opponent cooperate in the previous round, I will cooperate with probability P, and if my opponent defect in the previous round, I will cooperate with probability Q. So this is my strategy. Now in this notation we actually get back our known results. So if I go, means actually this means if I draw a PQ space, so in reactive strategy space these all will remain between, suppose this is P and this is Q, and these points 0 corner point is actually our deterministic strategies. This will be 0 1, this is 1 0, this is 1 1. Now let us see what this corner point means actually. 0 0 means I will defect I will cooperate with probability 0, that means I will defect if my opponent cooperate. If my opponent defect with probability 0 I cooperate, that means I will always defect. That means 0 0 is corresponding to all D. And again in this corner, that means 1 1 means no matter what my opponent does, I will cooperate with probability if my opponent cooperate, and if my opponent defect, I will cooperate with probability 1. That means this is corresponding to all D. Now this will corresponding to that if my opponent cooperate, I will cooperate. If my opponent defect, I will defect. This is corresponding to TFT. And this is not a known strategy. This is called a counterintuitive strategy. What is means what this player is choosing? Strategy is I will defect if my opponent cooperate, and I will cooperate if my opponent defect. So this is some counterintuitive strategy, and it has no name. So you see that TFT is a corner point of the strategy space of my reactive strategy.
Actually,
Yeah.
I mean, I don't know why, but then this
Hmm.
thing is not clear.
Okay.
So, 0 0. So whenever you write 0,
Hmm.
does this mean a defect? Or I mean, what this tuple 0 0
Okay,
signifies?
this double zero zero signifies this P and Q. So this is P and this is Q. So P equal to 0 here. This strategy means P equal to 0 and Q equal to 0. And what does P means? P means what is the probability I will cooperate if my opponent cooperate. So that probability is 0. And what does Q means? If my opponent defect, what is the probability of cooperation? That is 0. That means in both the cases, my opponent can only do cooperation or defection, and in both the cases with probability 0 I will cooperate. That means I will always defect.
Right. So in the, I mean, the meaning of Q is slightly,
Hmm.
confusing. That I mean, so P and Q both are the probabilities of
Cooperation.
making cooperation only.
Hmm.
Okay. Okay. Fine. Fine.
Hmm. So that is the case. Now this is the space. Now there is okay. Yeah. So this is the case. Now let us do one thing. What will be that if someone is playing that game? Now if some with probability some q and p1 and q1, suppose my now my strategy could be anything. Suppose my strategy is p1 q1. That means with probability p1 I will cooperate if I see you cooperated in the previous round, and with probability q1 I will cooperate if I saw that you defected in the previous round, and your strategy may be p2 q2. Now the question is what is the payoff I will get? What is the payoff I will get? Because the payoff will depend on, or expected payoff will depend on that on average how much cooperation you are doing and how much defection I am doing. So this cannot give you that level. So let us do that. So in on average how much cooperation and how much defection I am doing. So this means since our payoff depends on this state. So suppose there is a if you know little bit about the Markov chain, then I can use those language, but don't worry, this does not mean anything means does not mean anything new. So let me introduce that. So in this case, how much state is possible? Four state is possible, four outcome is possible. One is CC, one is CD, one is DC, one is DD. Out of the four, only one state you will get, and depending upon whether it is CC, CD, DC, or DD, the player will get payoff. Because if I go back to our payoff matrix, if CC outcome happens, then player 1 will get R, player 2 also get R. If suppose C D outcome happens, then I will get pay of S, and if D C happens, I will get pay of T, and D D happen, I will get P of P. So that means we have to know, if I play with this strategy, what is the probability of getting C, what is the probability of getting CD state, what is the probability of getting DC state, what is the probability of getting DD state. If I know these probabilities, I can calculate it on average how much I will get if I play this strategy. So that's why we want to calculate what will be the long term strategy, or what will be the means, if I play this game long enough, then at the means in the long run, what will be the probability of being means of being in the CC state, CD state, and DC state, and DD state. And to calculate it, we have to write a transition matrix. So transition matrix is this way. This will be a huge matrix. Let me write only few elements, CD, and how you can calculate the whole element. TD, here CC, this will be CD, this is DC, this is TD. Now here the thing is, the probability of going from CC state to this is from, what is the probability, I will write the element here, what is the probability of going from CC to CD. That in the previous round we both play C. Now what is the probability that in the next round we both will play CD? That probability is called the transition probability from CC state to CD state, that I am going to write. So let us calculate. So how we will calculate? So I am cooperating, and I will see what you played in the rush down. You played in the rush down C, then what will be the probability of playing C? This is
P1.
Yes, exactly. This will be P1. Now my opponent will see I played C, and what will be the probability that my opponent will defect in this round?
So it is Q2.
Q2 is the probability that if C observe my action is defection, but he sees my action is cooperation.
Oh, I see. So then it would be 1 minus P2.
Exactly. So that's how you calculate this transition matrix. So you can calculate all the transition matrix here. Now if you calculate all the transition matrix, means this is quite cumbersome, so means not cumbersome, you can write simply the elements. So I will not write the all element here. You will find the whole matrix in this that book that I am referred. So I will tell you what I will get from this matrix. Suppose this matrix is M, and suppose in the first step, the probability of observing is x. That means with probability x1, our state can be CC, can be with probability x2, our state can be CC, this is CD, DC, and this will be x3, this DD will be x4. So now let us again calculate one more, then maybe clear. Maybe this element, maybe DD and CD, maybe here. Let us calculate this element, then it will be much more clearer. Okay. Now in this here, that in the next step, my strategy will be C, and what I observe, my opponent what did is C, then with what probability I will cooperate, that will be P1. Now there is one, my opponent will defect, and when he will defect, after observing that I was played the previous round defection, what is the probability of defection if C sees I defected? That will be 1 minus q2. This q2 is the probability of cooperating after observing defection. So this will be 1 minus q2. So that's how you calculate that's how you fill the whole elements here. Now if in the initial round, suppose that my state space was like that, with probability x1 cc occurs, x2 cd occur, with probability x3 dc occur, and with probability x4 dd occur. Then if it was the case, then at the next instant, suppose at the 0th instant, and the next instant I will go to this state, x0 into m. So why x0 into m? So if I multiply x0 with this matrix, what I will get? So with x1 probability I was in CC, then what will be the means what will be the probability that CC will transit to CC? That will be CC. There will be is a probability that I will go to CC with CC. There is some probability, and CD, suppose this is probability alpha, this is probability beta. From the CD to CC, the probability is beta, transition probability is beta. From DC to CC, the transition probability is gamma. From DD, again there is a probability to go CC in the next round, that is delta. Then my probability should be in the next round of being at CC should be, I was with probability x1 I was in CC, and with probability alpha I will go to again CC. In the previous round I was in the x2 with probability x2 in this element, in this state with probability x2, and with this state 2, what is the probability of transition CC, that is beta, and with probability x3 I was there in the DC, what is the probability I will be there in CC, that will be multiplied by gamma and x4 by delta. And you multiply this row vector with this matrix, you will get exactly the first column as same as this thing. So that's how you can write the equation of the evolution equation of the probability of being in the state in this way. Now is it clear up to this much?
Yes, yes. And so I was just thinking of generalizing this entire stuff. So what would be the vector after, say, k number of the iterations of like this? So will it be like, say, I start with x naught initial and then capital M raised to the power k kind of the thing that I multiply transition matrix, say, k number of the times?
Exactly. So that we will after actually. So if we know that a m m's determinant means m inverse existed, m inverse exists, that means it is a regular matrix, that means all element in the m to the power m raised to the power k is positive. Then we know from there is a in the linear algebra there is a theorem for sure there is a eigenvalue 1 corresponding to this state x star equal to x m. So that means m star equal to m, that means this will be the stationary state of the m, and this means if I multiply x with m, if I multiply x with m, I will get back to the same vector. That means after infinite time, if I long enough, after infinite time it will reach to the stationary state. Is it clear? I know that it is not clear because the
So I could I could correlate this with the PageRank algorithm. Uh, yeah, so something similar to happens in the PageRank algorithm as well. That I mean, what should be the value of k kind of the thing that I get the original vector back?
Yeah. So yeah, you can think like that. What kind of the k value? Instead of k value, I will say that since this is the case, so you will multiply by m, again m into x, so you will get the m square into x also be x. So that means how much evolution will do, it will remain in the that set. It is similar to the fixed point that we are doing there, that in the doing for the dynamical stability case, x star is corresponding to the fixed point, and x bar is called this x. If there exists a x, it is called the stationary distribution. And if in technical term, if this Markovian chain is ergodic, then we know for the sure there is some condition for the m to be ergodic, and if m is ergodic, that means if m inverse exists, you for sure you
So I could not. So this term is new for me. The term which you just now ergodic something
uh,
that I do not know.
okay, this to introduce to ergodicity of a stochastic matrix, that matrix we have written with the probability. So this is a term from the non-equilibrium statistical mechanics, that is called the how the Markovian chain operates. So it is not a means it is not means I cannot prove these things, and I can only say the definition of the Markovian uh, the ergodic Markovian chain, but don't get involved with those. Only know that if m inverse exists, that inverse existed, then you can get a stationary distribution. That much is
So the eigenvalue is lambda is one here.
eigenvalue.
Eigenvalue is one here or what? I mean,
Eigenvalue is 1. Yes. If m inverse exists, then there is a theorem that guarantees that there will be a eigenvalue which is corresponding to 1. And that since that existed, so we know that there exists a eigenvector normal, and we normalize it, and this will give us the probability that the stationary probability after, if we evolve the system in, if I wait long enough, we will see the system will converge to this x bar. Now this x bar is, now there is another way to came up to this x bar without this much thing. So let us do that thing, that is very simple and intuitive. Let us do that thing. So in this is the general way for the general thing, but it only works for when the m inverse exists, and that is the thing. Now let us do simplest thing the possible. What will be the value of x bar? Now what will be the probability of cooperating in this round? Let's see, what will be the probability of cooperating in this round? With p1 probability, I will cooperate. Okay, let me do in this way. Suppose, then you can suppose cn is the probability of cooperation, probability of cooperation, probability of cooperation of mine. Then what will be the probability that I will cooperate in this round, nth round, if in the n minus 1 round my opponent, suppose n prime is the probability of cooperation of opponent, this is focal player. Now this, if my opponent in the previous round cooperate, then with probability p1 I will cooperate, and instead of cooperation, if it defect, what is the probability of defection? C minus 1 prime into q, that will be probability of defection. So that means here p1 minus q1 into cn minus 1 prime plus q1 will be the probability of cooperation, if I knows that my opponent cooperation probability is cn prime. In the previous round is cn minus 1 1 prime. Now what is the probability that my opponent will do cooperation at the n minus 1 round? What is the probability of that? If with probability p2 he will cooperate if he observe cooperation and n minus 2 round, plus he will do cooperation if he observe the defection in n minus 2 round. So that means p2 minus q2 into Cn minus 2 plus Q2. So let us define P1 minus P2, P1 minus Q1 equal to R1. So that means here R1 into Cn minus 1 prime plus Q1, and here again then R2 plus R2 Cn minus 2 plus Q2. Is it clear?
So, so why are we writing this as Cn minus 1 prime? Instead of the Cn minus 1 prime, we could have simply written it as Cn minus 1 only. I mean, why to use prime kind of a thing?
Okay.
Because this will, because yeah, if we simply write Cn minus 1, then this will result into a difference relation kind of the thing which we can solve later on, probably.
Yeah, but you see that I am writing what is the probability of my opponent, means I will not cooperate by observing my move in the previous round. I have to observe what is the probability of my opponent did cooperation in the previous round.
Oh, yes, yes, yes. I understood. Yeah, fine.
But you are correct. You are correct where means the direction we are heading, because this Cn minus 1 could be written down in terms of my cooperation probability in the previous two round, because in the previous round the what opponent will do, when the opponent did what he had observed in the previous of that round of my cooperation probability and n minus 2 round. So what is the cooperation probability of my cooperation probability of n minus 2 round multiplied by p2 and q2 multiplied by the probability of defection? Is it clear?
Yes, yes.
And here this is the opponent's cooperation probability and n minus 1 round. It should be related to the my cooperation probability at n minus 2 round. Now I simply put this Cn minus 1 here. I'll get a recurrent relationship, that will be R1 in place of Cn minus prime. I'll put this R2 Cn minus 2 plus Q2 Q1. Now we'll find Cn equal to R1 R2 Cn minus 2 plus R1 Q2 plus Q1. This is a recursive relationship. Now this is the map. Again, what is the fixed point here? What will be the fixed point? Fixed point will be at which point this Cn will become exactly equal to Cn minus 2, because after that if it hit that point it will not move, it will not change anymore, that will be fixed. That is, if it remain in that state it will remain forever. So that means suppose this C star follows this relation, then instead of C just write C star R2 C n minus 2 plus R1 Q2 plus Q1. So this means C star 1 minus R1 R2 equal to R1 Q2 plus Q1, and you will get C star is actually R1 Q2 plus Q1 by 1 minus R1 R2. Is it clear? This will be my final final strategy. Or
Yes.
yes.
Yes, yes, it is clear to me. Yeah. This is the optimal value wherein what would happen that the fixed point will get achieved with the specific values of the P1 Q1 and the P2 Q2.
Yeah, yeah. And again, for this also you can do the stability analysis whether or not that it will, means there can be exist a point where if somehow it reach it will stay there forever. But we can ask the same question here also, that whether or not this point will be stable. Then we have to see the differentiate, we have to differentiate with respect to Cn minus 2 here, and see whether or not it will become less than 1. Okay, so here, so this is the case, you are right, this is the point, is called the fixed point, this is the fixed point. Now we know the fixed point, but we have to again calculate the stability, means whether or not it will achieve by our dynamics. If we run enough, if this fixed point is stable, then also, then actually my dynamics will go toward that. Otherwise it will not go. So previously whatever we done for the differential equation, now here we get a map. Now for the map we have to calculate cn minus 2, and means differences of cn with respect to cn minus 2, and it will give you r1 r2, and this is for map. Whatever we done for the differential equation, now we want to check the stability for map, and it comes out that this quantity, this is called here Jacobian, and since it is one dimensional, this is the eigenvalue, and for the map this value should be r1 r2, the modulus value of r1 r2 should be, means has to be less than 1, then only we say there's this point, this fixed point, this fixed point c star r1 q2 plus q1 is 1 minus r1 r2 is stable, stable fixed point. Or I will say this, if I run my system, the probability state phase in the in the in the Markovian state, this state will achieve with this state will certainly achieve if r1 by r2 is less than 1. If r1 and r2 is become greater than 1, then this fixed point will become unstable, and the system will never reach to the this fixed point. So that is what we want, that is what is there. If any question is here, you can ask me.
Yes, so it is. I mean, it's clear. It's
Okay,
clear.
yeah, then it is fine. So one, with this one relation we also need that r1 r2 is less than 1, then we know that uh, the probability of cooperating, no matter whatever my opponent does, is this. And what will be, let's calculate similarly, what will be the in the similar sense, what will be the probability of playing my opponent's cooperation, that will be r2, that will be r2 q1 plus q2 1 minus r1 r2. So that will be the cooperation probability my opponent. So let, in place of c star, let write it s1, and let's write this, the opponent's probability of cooperation is s2. Now this will be the probability where the system will go automatically. Now then, what will be the probability of observing cc state? That will be s1 s2. What will be probability of observing cd state? That means I play cooperation, my opponent is defection, that s1 1 minus s2, and I defect and my opponent cooperate, that is probability s2 1 minus, sorry, sorry, this will be 1 minus s1 into s2, and what is both of us defect 1 minus n, 1 minus s, 1 minus s2. So this will be my, this is the probability of both of us cooperation, both of us, one of us cooperate, one of us defect, I defect, you cooperate, and both of us defected. This is the probability, this is the probability, or this is the state where the system will automatically go.
So I have a
uh,
query here
uh,
that do we have a generalized form of the S1 and S2? Like say, if instead of the two strategies only, say if I have been given T number of the
hmm.
strategies, then do we have some kind of the generalization available for the S1 and S2?
uh, you could generalize, but I, since I never came across some you are saying that in place of two player, you are saying that multiplayer repeated game and
So
generalize.
no. In my query, the players are two only, but then they have got k number of the strategies. Like say, So apart from the cooperation and the defect, if I've got some other
Okay.
action as well, and moreover, this could easily be extended to the, you can increase the number of the players as well. So do we have some kind of the generalization available wherein we can design some transition matrix for t number of the actions possible, and for the k number of the players?
Uh, for my knowledge means I never came across such kind of things, because you see, when you increase the cooperation depiction, maybe you put another thing, the cooperation depiction and something, maybe you
But then
can.
but then I was also thinking that, say, if there is another strategy, like say, apart from the cooperation and the defect,
Hmm.
there is another strategy. Let us call that strategy at say capital E.
Hmm. Hmm.
So then capital E can possibly be represented as some combination of the C and D kind of the thing. That there is an strategy E. Say so then this would be that if I make cooperation 40% of this will involve say 40% of the cooperation, and then 60% of the defection kind of the thing.
Acha, then you can see that that formalism is already there, because that strategy is already there.
Yes, that is there. That is there because this entire thing is stochastic kind of
Hmm.
thing. Yes, yes.
Other than
Yeah.
that, if you want to came up with altogether some other strategy which is different from C and D, that I don't aware of that there is any concrete result for that. But I think you can do it, but it needs a little bit hard work maybe. So that is the thing. Then we can calculate if one strategy p1 q1 and other I playing with strategy s p1 q1, and you playing with the strategy q2 q2, then what will be the expected payoff I will get? The expected payoff I will get, that with probability s1 s2 I will get payoff r, with probability, sorry, with probability s1 s2 I'll get P of r, with probability s1 1 minus s2, how much payoff I'll get? Because here I cooperate and you defect, then how, what payoff I'll get? I will get the payoff, sucker's payoff, because I will get s. And here I defect, you cooperate, then I will get temptation payoff, that means 1 minus s1 and s2 I will get t, and with here both defect I will get p, the punishment I will mind s2 into p. So on average I will get this much payoff. Now since I know the my strategy's value, so I can write expected payoff exactly if I know the strategy. Now that's how we want to, since I know this is suppose s1, this is s2, so I know what is the expected payoff I'll get if my strategy is playing with against yo, this is the, suppose this is the thing that I want to, this is equal to this s1 s2. Now we can actually calculate what is the ess if, instead of, means we know the definition of ess, if s is the ess, suppose some strategy s is the ess, then the ess means that expected payoff should be greater than all other strategy is for all other strategy, all other strategies, and this is the first condition of ess. And the second condition, if somehow these two equal, these two, sorry, let me write, since we know the expected payoff, now write the condition for ess. So condition for ess, on average, this will be my fitness. So if the fitness of the A star is greater than, if a resident population playing with a resident population, the on average fitness he is getting is much greater than the fitness that mutant gets playing with resident. If it is greater than that, then A star is ESS, and if somehow E A star comma A star is become equal to E s comma a star. Then we have to check next condition, that is what a star will get in play with mutant population. If this for all s, then a star will be ESS. So now we have to check this condition. Now we don't want, means since in the strategy space there will be multiple strategies, then we don't want to analytically see these things. But one thing we can do, we can check it numerically. Now what we'll do, we'll check it numerically, but the there was not enough time available to write down a code. In the next class I will write a code, code written in Python, and will show you what is the what is the result that is coming. But let me tell you that what result we will expect from those numerical analysis. So what we will do is
So actually, this ESS, so when you compute this, when you verify things for ESS, well, that is not that much clear to me, except that I could understand that if something is in ESS, then it is already there in the Nash equilibrium. And the second thing is that whatsoever modification we make in the strategy is not going to improve the correct situation. But then when you write the equation to prove something in the ESS, like say here you wrote say S star for the equality case. So this, I mean, these two equations are not clear. So it would be really helpful if you can,
okay, this is the not equation, this is the definition of the ESS. So ESS means what? So ESS means what? If we go back, and there is, I think, what does the ESS definition means? So if A star is the resident population, now if some mutant comes with strategy S, now I will say, does this strategy will get much payoff or fitness on average from the resident population? If it does not, then it cannot invade the whole population. Then I will say A star is the ESS. So is the general
yes.
is the general definition of the ESS. So
Yes, and then what happens when it becomes equal to? Then what else need to be verified then?
then we have to verify that what payoff on average the resident population gets with playing a mutant, that should at least greater than what mutant is getting with playing a mutant.
Right. So then what this E, when I write E and then S star comma S star, so what does it mean? That who is playing which strategy? I mean, how to model this as a game kind of the thing?
This here, this is S1 S2. I have written this is S1 S2, E S1 S2. So I think it is not clear. So this is the expected payoff of E S1 and S2. Here the strategy S1 means this, S2 means this.
Like say in the case of the resident and the mutants, so what, I mean, who is playing the role of S1 and who is playing the role of
A
S2?
star is the resident. Here A star is the resident. Means he is the first. Whoever is the first is the means A star is the resident here, and the payoff I am talking about here, the payoff of the player who is playing S1.
Uh, I see. So initially in the left hand side of this equation, does this mean that the strategy being played by the resident among themselves?
Yeah.
Among themselves? Okay.
Yeah. Among themselves, and how much they get on average, yes.
Okay. Okay, yes. Now I understood. Yeah. Thanks.
Okay, that is the case. Now, as we know in the previous case, there is a direct relationship between the replicator dynamics and these ESS. So if I know for sure if there is some selection is going on, and if replicator dynamics select some strategy, we know for sure that strategy will be ESS. That we have checked for the fogged up situation, and that will be also Nash equilibrium also. If replicator dynamics select some strategy. Now that's why what we will do, or general idea, but general idea is, so for taking strategy, we will take P1 we'll choose PQ. The PQ is my strategy. So P will be a random number between 0 to 1, and Q also a random number between 0 to 1. So now I will take 100 such tuples, 100 such numbers. So 100 P and Qs. So 100 strategy will be there. Now with 100 strategies, I can calculate, since I know the 100 strategy is P1 Q1 value, I can calculate the expected um, expected value of their one. Means if some strategy, suppose one strategy is P1 Q1 and another strategy is P2 Q2, and using this relationship, this E S1 S2, this is S1, suppose this is S2, I know exactly how much a player who is playing strategy S1 and interacting with S2 will get on average. So I know now this will be a fitness of S1. So this will be the fitness of S1, P S1 comma S2. Now the fitness of the S2 will be P S2 S1. Now here I am not talking about 100, I will generalize to 100 in the numerics, but let's talk about the only two strategies. So S1 S2, and suppose in the population there is a x fraction of individuals who are playing this kind of strategy, and in the population there is 1 minus x fraction of individuals who are playing S2 strategy. Now then we can write what is the average fitness of the population, that will be f S1 minus plus 1 minus x f S2. Now we can write a replicator equation, x dot will be x into the fitness of S1 minus 5.
S1 minus 5.
Exactly. So this is for the two individual case. Now since I am talking about, I will generalize this. I will take hundred such strategies, and then for the 100 equation I will I can write 99 100 such equations. So 99 replicator dynamics, that will look like Fi. This will be f of Si minus summation of I equal to 1 to n, or 1 to n x I f Si, or if j maybe j, this is j. So that's how we can write in principle such equations, because we know the strategy, we know the fitness. We if we now if we know the initial frequencies of the population, suppose I have 100 types, now I have 100 types of strategy in the population, and if you think that all the strategies are equally abundant, suppose in the population the frequency of each strategies are equal, that means S1 frequency will be 0.01, and S2's frequency will be 0.01, and so much. So S100 frequency will be 0.01. So everyone's frequency is 1. So from this equal abundance case, if we evolve the system, now we whatever we left with, that what will be the fate of the system, that we want to observe. So the code is not present with me now, but I know the result. So I will show you, means in the next class I will show you the result that is coming from the code. Now I will summarize that what you will get if you run the code in computer. So you will find that if one thing you will find, if not a TFT like, if not a TFT like strategy, if there is no strategy is present in the P1 and Q, these all 100 strategy which is close to TFT, if TFT is not present, you will find all D will all D will invade the population. You will see that all the strategy will all the population in the long run will become will adapt or will become all D strategy, means all the individuals will become all D. That is the first case. And the second case, you will observe, if there there exists some strategy which is close to TFT, then all d, now you find that at up means all d will be there for some time, then after some point of time the TFT will invade the all d population, and TFT, the frequency of the TFT in the population will increase, and after some point of time, you will find that the TFT is not the case which is actually whose frequency become one. You will find that a strategy whose strategy is P equal to 1 and Q equal to 1 3 like strategy will ultimately you will see in the population when the frequency of this kind of strategy will become this kind of the frequency of this kind of strategy will become 1. So in the long run you will find not TFT not only if TFT is present there, you will find some strategy which is called generous TFT. Why it is called generous TFT or GTFT? Here you see GTFT, you see why it is GTFT, because you see with probability 1 I will cooperate if you cooperate, but with probability 1/3 I will defect, I will cooperate if you defected in the previous round. That means if you defected 3 round I will means out of your 3 defection I will cooperate only once. Oh, let me this why in the TFT case for P equal to 1 and Q equal to 0. So if you cooperate, I will cooperate, but if you defect, I will also defect. But here it is not the case. Here is the if you cooperate, I will cooperate, but I am generous, so that's why I will forgive your 3 defection. I will forgive your 2 defection, and out of 3 defection, I will cooperate once. So that means I will cooperate with royalty 1/3 if you defected in the previous round. And you see, this GTFT is actually correct one very one two slide errors that cannot be taken care by the TFT, because in presence of slide errors, we find that TFT, the on average pay of the TFTs get is become very less, and it becomes like same as one player who is playing his strategy by choosing his strategy by tossing a random coin with probability half. But these GTFT could handle, let us take a situation GTFT could handle the situation error, because C it will play C. Now if some error happens D star, it will forgive this D star, it will play C. Now since this happens, this will again play CC. So somewhere error happens CC. So you see here in the long run the GTFT will always get a payoff which will be closely equal to the R. Whether in TFT against TFT will in if there is some error, they will get on average payoff that will be RST plus. So that's how this GTFT is actually a good strategy, better than TFT. And in the presence of TFT, GTFT could invade a population of all D. Now, is why this Q is 1/3? That is the question. Now, the simple reason is that uh, in the next class, because the time no time is left, so in the next class I will show you the code, and um, I will present why the Q's value is 1/3, because you see Q need to be such that it can invade the all D. Otherwise, if I increase the value of Q, means if it become too much generous, then it cannot invade all D altogether. But uh, if if Q has a bound, and that bound you can calculate in who what will be, let us calculate it, it is very simple. So let us calculate here. So GTFT and all D. So this is defect. So it will start with cooperation. Now, as soon as he see defection, with one third probability it will, or with q probability it will cooperate, and with 1 minus q probability it will defect. So that means in the first round the GTFT will get in the first round, it will get, since defection it will get a sucker's payoff, but in the consecutive round sometimes it will get, with q probability it will get sucker's payoff, because in the q probability it will cooperate, and in the other time 1 minus q probability it will get a payoff p. Now, and what Aldi get? Aldi, so maybe I do some Aldi get. Oh, let's do it in the next class, because something I think I missed something here. In the Aldi it should get t plus qt plus 1 minus q p. So I missed something, maybe I will do it in the next class, why there is some upper bound of q, and I will show that the results of the code, if I run the replicator dynamics for 100 100 species, 100 not species, 100 strategies, what it will, what result it will show, what result it will, we will observe. So that's it. So if you have any question you can ask me, or maybe we can meet again tomorrow.
So because I am unable to open notes which you shared in the Google Drive, because the size of each note is more than 100 MB.
Okay.
So I think that the size of notes cannot be that large, because then it says that it is unable to scan the document and then blah. So is it possible for you that you save these notes in the proper format and then share it in the Google Drive?
Okay, proper format means I have shared it in PDF format,
But the size of each note is more than 100 MB. How is that possible? I mean, 120 MB, 140 MB.
okay, let me try it.
Right.
Then maybe I will see. I mean, if it.
Yes.
Okay, let me try it.
Yeah. So if you can compress these notes, then share.
Okay, okay, okay. Then
Yeah. Yeah. Thank you so very much.
okay.
Tomorrow at 11:30.
Yeah, yeah. Okay.
Thank you.
Thank
Bye.
you.